Welcome everybody to our usual colloquium. So today we are very happy to have Jaron Kent-Dobias with us. Yeah, I was mixing the two pronunciations. So as probably many of you already know, he's one of our Simons Papez Fellowship. So let me, as usual, introduce our speaker. So he got his PhD in 2020 from Cornell, and then he started the usual postdoctoral journey. He was in CNRS for 2 years, from 2020 to 2022. Then he moved to Italy, to La Sapienza, for other 2 years, 2022, 2024. And finally, he joined 1 month ago us here in ICTP-SAIFR. From his CV, he defined himself as a physicist studying the statistical mechanics of critical non-equilibrium and disordered systems, right? Yeah. And today's talk is about that. And the title is Fitting with More Parameters Than Data Points, Topology of the Solutions to Overparameterized Problems. Jaron, the floor is yours.
Thank you, Dario. So I'm going to, this talk basically has 2 broad parts. There's a part where I'm going to talk in very generic terms about other people's work, kind of introducing the sort of problems in this field that my work is trying to address. And then I'm going to talk in the second part specifically about a project I've done attempting to, advance this field. So imagine that you want to fit a function. You have some data. It might come from some true underlying function. In this case, you might guess what that function is. But let's pretend that you don't know what the function is. You need to think up some way to approximate it. The standard way to do that is with curve fitting by least squares. So in the linear least squares formalism, you pick some set of trial functions, of basis functions. So in this case, you have n different basis functions, which are the first n Legendre polynomials. Polynomial fitting is a standard choice of way to go. And then you want to approximate the ground truth function, which you don't know, by a linear combination of your basis functions. Right? And that linear combination is parameterized by parameters, the a's, of which you have n, 1 for each basis function. And given the m data points that you have, you want to minimize the sum of squares over the difference between the value of the data at each point minus the trial function. This sum of squares, this chi-squared function, when you find the minimum with respect to the parameters, given fixed data, you have your best fit. Right? This is something we all have probably done. So the standard, let's say, thing you learn when you start learning about best fits is that the results can depend very heavily on how you choose the number of functions to involve in your basis. So if you choose too few parameters, too few basis functions, you don't describe the underlying data and all its complexity. You miss some essential features. And a statistician would say your fit is biased because it misses systematically some features of the data. Or if you have way too many parameters, here the same number of parameters as there are data points, your chi-squared value is 0. You go perfectly through every single data point. But in the space between, you do a completely awful job. And it's not very good. I mean, you don't do a very good job of describing the underlying function. Whereas if you find just the right intermediate value of parameters to data points, you balance your chi-squared at some intermediate value, you see that you do a good job describing the function and also not too far from the data that you have. And you can quantify this if you know the underlying function. So in this case, of course, we know the underlying function. And you can quantify this by computing something like the mean squared error. So you compare the value of the true function to the guess that you've made here as a function of the number of parameters you have in your fit. Remember, our fit was to 40 data points. And so a very typical thing that you see when you look at this kind of plot is that the performance of your fit starts decreasing as you increase the number of data points. And then it has some intermediate range where it does an okay job. And then finally, as you approach a number of parameters equal to the number of data points, things become awful in an extremely crazy way. I mean, this is a log plot, so things explode in a very bad way. And this reflects a kind of trade-off in the fitting procedure between bias, having an expressive enough function to actually capture what's happening with the data, and variance, which is how sensitive the resulting fit is to small changes in the noise. Now, all of this story of curve fitting is borne out in the modern usage of machine learning. So machine learning in its actual practice is essentially a kind of nonlinear least squares fitting. Yes, Nathan? In the talk I'm going to give, so typically the way that you involve error bars is by weighting the data because I'm talking about the overparameterized regime, so the fits that I'll be exploring in a small number of slides will perfectly go through every data point. In this case, the weighting is basically irrelevant. And so error bars could play a role, but for the sake of this talk, it's not very relevant. Though in fact, the amount of noise is very relevant, and I'll get to that in a few slides, in fact. So in machine learning, you have data, you have many data points, say all of the images you find on the internet. And those data also, unlike the curves I've been showing, are in very high dimensions. So an image has, I don't know, 1,000 pixels by 1,000 pixels. You have very, very many dimensions of each data point. So that's different from what I was showing. You have some ground truth function that you don't know and you probably could never know, right? Like the probability an image contains a cat. How would you write down that function? How would you even start to reason about it from first principles? It's quite beyond us, I would say. But instead of, so because you don't have no idea what the truth function is, you use a guess, which is typically something like a neural network, which is just some very big nonlinear function. Typically something like repeated application of matrices. These B's are matrices, so linear transformations of the incoming data with piecewise nonlinearities applied each time. So and then all your parameters are all the values of the numbers in these matrices. This is a simple kind of neural network. So, okay, but it's the same procedure. You just want to find the values of these matrices which make the data you have, reflect the test function you want to fit the best. So, of course, chi-squared exists. People use it. They call it the cost function or the loss function. And the best chi-squared, the value of chi-squared at the best fit is known as the training error. It's the amount of, say, deviation you still have in your data at the end of the fitting procedure. And of course, we don't know the real function, so computing the mean squared error as I described it is impossible, but typically people reserve some data that they don't use for training, and then they can test how good their fit is by seeing if the function that they fit does a good job of classifying the things that they didn't use in the training procedure. So this gives you an approximation of the mean squared error, and they call that the test or generalization error. But a very key difference to the, university level fitting that I talked about before is that in machine learning you have a lot more parameters typically than data. So you have a set of images, maybe you have, 1 million images from the internet, but okay, the modern models use tens of billions of parameters for their matrices. And so this seems very unintuitive. You might think, okay, well, you're going to get situations like the one I saw on the right in the previous slides where you overfit in a crazy way, and when you try to look at new images between the ones that you have in your sample, they're going to be, way off. But actually, you can already see...
What is the relationship between N and L?
So
L is the number of matrices, right? And each of them is M by M, roughly speaking.
Sorry. M, I'm going to always be using as the number of data points.
Correct.
N will always be the number of parameters in the fit.
Correct.
And so it will be the total of all of the parameters in the matrices.
Right. And so how is it related? Because L is the number of matrices that you have, right? So
L is not going to be relevant at all after this slide.
Fine.
So the depth, the structure of neural networks I'm going to leave that behind. I'm going to study more fundamental problems in the least squares setting where things are easier. So machine learning uses a lot more parameters. You might think it's a disaster, but in fact it's not. And we can already see that it doesn't have to be a disaster with simple linear least squares. So here's the same, sorry, yes? You can all take in this slide as Ricardo asked this question.
Yes, sorry. I have some resistance to adopt machine learning methods for the following reason. We might be very naive because I know very little, so you might tell me I'm too naive. So the chi-square, I know within some assumption how to assign a probability to it. But the cost or loss function, what do I do with that? It's not a probability.
I agree. It's usually quite ad hoc. You might say if you're saying probability an image contains a cat, maybe you have a bunch of people that you survey and they say, oh, maybe that's a side of a cat or a side of a dog in this image. I give it 50-50 and you try to approximate this. I don't know. The point is, I'm not here to say that this is a good method necessarily for certain data sets that are difficult to describe in certain ways. I'm here to say that It's a method that for some things works in an unexpected way, and we're going to explore why it does this, like the mechanisms behind. I mean, we'll see in these examples, let's say. It might become more concrete. So here, for instance, is the same data I showed you before, but now on the very far right, I've fit the data with 80 parameters for the 40 data points. Of course, having 80 parameters, it goes perfectly through all of the data points, but this time by the normal statistical quantification of whether or not it's a good fit. It seems to be a good fit. It has a low variance as you change the data points noise. It doesn't move a lot, and it has very low bias. I mean, it goes through all the data points. And if you evaluate the function at points in between, it returns a reasonable value. Now the question is, if you look at the plot, for instance, now the same plot I showed you before of the mean squared error as a function of the number of parameters, you see that you have a huge catastrophe as the number of parameters equals the number of data points. This is called the interpolation limit. But then the mean squared error descends a second time. It's like, in machine learning, people call this the double descent curve. And you saturate at a value of the mean squared error, which is a little above, but comparable to that you get for, again, this is just polynomial fitting, linear least squared fitting, with the previous best fit I showed you.
It doesn't look, looking back, I would still say that the case in which n is 7 is still slightly better than 80.
I agree,
but
but
that is a log-log scale, so probably you don't see the slight difference.
No, it absolutely is. It is better there.
But
we'll get to some examples where it is better to be in the overparameterized limits. But for
because from the curve it doesn't look like, right? In the other curve, okay.
Sorry, here.
Yeah, here. They look at the same level. But they are not, and the difference is important because this is a log scale. Am I
It's
right?
a log scale,
okay.
yes. It's
So
a log
this
scale.
is okay.
No, it's true. So it is slightly better, the fit at n equals 7. We'll see some examples where the overparameterized is better, but this is, I'm starting with the most basic possible thing here. So
I don't know what fit means. I thought if it goes to all
this is an
data
important
points-
question. We get to the next slide.
Okay, go ahead.
So this is a bit misleading because unlike in the case where you have fewer parameters than data points, there is not a unique way to put an 80-degree polynomial through 40 points. You have to choose from a collection of solutions which go through all 40 points. So how do you do that? So, this isn't about how you do it. This is talking this out. So in the underparameterized case, it's unique, right? It's a convex problem for linear least squares, so there's one solution. Whereas in the overparameterized case, you have m constraint. If you want chi-squared to be exactly 0, it's like having m constraints in your n parameters, which gives you a manifold of a certain dimension. So you have a continuum of solutions on this manifold, which in linear least squared is actually just literally a hyperplane because it's a linear problem. And the question is, I can show you here a collection of good solutions which are different from each other in, are they moving here? Yeah, you can see the slightly moving on the ends. A collection of good solutions which are slightly different from each other. And I could also show you a collection of bad solutions with 80 parameters, which are also all different from each other. And the question is, what leads to good solutions versus bad solutions? Good solutions in a sense. Because I mean, there are some ways in which these solutions are unsatisfying, let's say, but they're good in other ways. The answer is actually very simple. To generate these plots, I did the stupidest thing you would possibly do when faced with the task of optimizing a function. I used gradient descent. So gradient descent, what do? You start from an initial condition. You follow the minus gradient of the cost function, or chi-squared, until it becomes really small because you've reached a minimum. And so in this case, you can think of this plot here as a representation of the parameter space, the A's, and the best, the perfect fits with 0 chi-squared are some hyperplane in this space. And gradient descent will take me from somewhere in the initialization space to the hyperplane. Now, it turns out there's been a lot of work. So the important question is, how does this mapping work? What happens from the initialization to the hyperplane? There's been a lot of work by mathematicians proving things about this recently, which have shown that how you initialize the gradient descent acts like an implicit presence of a regularization in the cost function. So if you initialize gradient descent from a place that has a very small norm in the vector of the parameters, then the gradient descent trajectory will tend to take you, with very high probability, to a place on the manifold where it's as if you did the fit with a regularization of the norm of the parameters. Likewise, if you start the gradient descent in a place with a high norm for the initial condition, with overwhelming probability, you are likely to end up on a place in the manifold with a high norm of the parameters in that space. And it turns out, for this problem, the low norm solutions look good in, let's say, the senses I was saying, whereas the high norm solutions look quite bad. But
is it immediate to see why low norm means good and high norm means bad?
So it's very dependent on the structure of the problem at hand. Obviously, if you choose a different basis that has, different properties, you may have not this property. But the fact that we've been seeing in many examples that are common in what you see in curve fitting machine learning is that, let's say, simple bases, like Occam's razor style bases, tend to have this property. So like, if you start with functions that are simple in some way, you get this kind of thing. If you start with kind of bad bases that we would think of as unnatural as physicists, you don't have this property. So this is one very interesting fact. So just the algorithm, the simplest algorithm you have, the algorithm that no one knew this before they started doing machine learning. They just, were trying to compute things and fitting random functions to random things and using whatever algorithm they had at their disposal. But luckily for them, in hindsight, we know they were helped by the fact that the algorithm itself, even though the problem is overparameterized, projects you into an area of the solution space that works well by the algorithm's properties, in fact. So an important part so I'm going to start adding features here, more things that make machine learning work. Another feature in this overparameterized limit is the choice of basis, as I was saying. So I've been talking about the polynomial basis, Legendre polynomials. You could also choose a different basis, for instance, a bunch of spiky functions. This is kind of more like a neural network in a qualitative way. And in fact, if you choose the basis of spiky functions, what you see with the polynomial basis, which is kind of bad fit, good fit, very bad fit, okay fit, kind of goes away. With the absolute value basis, you see a bad fit, a reasonable fit, a sort of good fit, which is literally just linear interpolation of the points, and then a fit that's about the same as the linear interpolation of the points. And in this case, changing bases, we see that the spike at the interpolation limit, when the data equals the number of data points equals number of parameters, it gets flattened out. It basically goes away. And in fact, in real machine learning models, neural networks and things, you don't see the double descent. You just see a single thing that goes down. But you might ask, probably, it's burning in your throat right now, if the best you do after the interpolation point is very similar to linear interpolation of the points, why are we bothering with overparameterization? Why not just linearly interpolate? Well, there's kind of two answers for this. So one answer is that the data you have in machine learning situations is very high dimensional. And if you want to do an interpolation, typically what you would do is you'd make a grid. And then you would start connecting points in your grid and say, okay, between these 2 points, I need to vary the function like this. Between these two, I vary it like this. Between these two, et cetera. The number of points you need to make a grid grows with the dimension of space like an exponential. For a hypercubic grid, to make around 1 point, you need 2 to the dimension of space. So for images, which are 1,000 by 1,000 pixels, you need 2 to the 1,000 by 1,000. This is not how much data. You have a lot of data. You do not have that much data. You have, in fact, in machine learning cases, you can consider as being extremely sparse, extremely sparse in the data you have. And the other thing that's true of machine learning cases, so now we're going to, this last example here in this section, we're going to go from a case where we have a kind of dense data that is fairly noisy to a case where we have sparse data where the noise is quite low. And in this case, when we look at the sparse data and we do the exact same procedure I showed you, now with the absolute value basis, we see that going into the overparameterized limit starts to beat the interpolation points. This is literally just starting from zero initialization and doing gradient descent. I haven't changed anything. I haven't picked in a fancy way this last curve here. But this implicit normalization just so happens to do a very good job of making a kind of Occam's razor approximation of the curvature of the cosine function. So for the kind of natural simple functions that we're trying to describe with these systems, it seems like, and for the kind of guess models that we have, like these bases, it seems like you do a better job to start with too many parameters and let this interpolation kind of work. Again, here's this plot again. So for this, if you look at the mean squared error as a function of n, this is no longer a log plot. So it was really impossible not to have a log plot for that first one, because it really goes too high. But here you see the best you do is above, by an order of magnitude, let's say, in terms of the performance compared to the base truth function. Now, well, there's one more feature that we don't know completely. In fact, we don't know in most cases why these sort of models work and the data, and actual images and things. But there's one more feature that we do know is important, which isn't very relevant for linear least squares. And that's another feature of the algorithm. So in fact, I've been talking about gradient descent this entire time. But in practice, nobody uses gradient descent, because gradient descent is a very expensive algorithm. At every step to compute the gradient, you have to compute this chi-squared, which is a sum over all the data points of an expensive function. And so typically, not typically, 2 decades ago, when people were figuring these things out, not why they work, but how they work, they didn't want to bother computing the whole gradient because it's very expensive. So they took a subset of the data and they computed the gradient with that. And in the next step, they took a different subset of the data and they computed the gradient with that, et cetera, et cetera. And this algorithm is called stochastic gradient descent. And if you compare its performance with actual gradient descent, where you do a more expensive thing to have a more precise gradient, you find that the stochastic case works better. It goes faster to the bottom, and it produces better results. And so this is another important feature of the performance, kind of how these different methods shape what you pick of the manifold of perfect solutions. And there's a kind of,
I guess what you said can depend quite strongly on how large or small are the batches over which, right?
Absolutely,
Are
yes.
there rule of thumbs in deciding?
For very simple problems, you do have people with have some results on these sort of things, but mostly it's just engineering. You pick the one that works the best. So I'm just going to give a very simple cartoon for how we're beginning to understand why this works, but this is very kind of early understanding. This cartoon is that when you have the space of let's say this is a slice of the cost function of chi-squared, and you can see that there's solutions that, there's some solutions that have like a wide, large manifold, and there's some solutions that are isolated and skinny. And when you do gradient descent, you simply go down the hill, very deterministically, following the twists and turns very, very carefully until you reach the edge of the sea of, the manifold of solutions, and then you'll stop immediately, right? Gradient descent has nowhere to go once you hit the edge. Whereas stochastic gradient descent, it's basically, people have actually shown that in many ways it acts like a Langevin process with correlated noise. Here, you have a noisy process. Sometimes you go uphill, sometimes you go the wrong direction. You mostly go downhill. But because of the noise, you tend to end up in a high entropy part of the space of solutions. And it so happens that in the kinds of problems we study, with the kinds of basis functions people use because they work, the high entropy parts of the space of solutions, the parts that are, if you do a random walk on the manifold of solutions, you are overwhelmingly likely to end up, these are where good solutions are, compared to on the edge of the manifold where you have mediocre solutions. And of course, if you find very isolated points, well, in practice, you never find isolated points. Another kind of blessing of, nature in this fact is that isolated points are extremely difficult to find with algorithms, any algorithm you like. And they also have to be horrible solutions, so it's good we don't find them. And so these various features, the properties of the function itself that you're fitting, the properties of the data, its high dimensionality, its sparseness, the properties of the algorithms, like gradient descent and its regularizations, and stochastic gradient descent, and the noise it adds to the process, these all seem to conspire together in a way that we are still coming to understand, to make overparameterization work very, very well in machine learning problems.
So does horrible solution mean that if you perturb it, it looks something very different? Or what is a horrible solution?
Yeah, so you can think of these as being like the solutions that have very high variance, right? Because this shape of this whole thing depends on the noise and the function. So this, you imagine if you change the noise a little bit, this point will move quite far. And that's a high variance solution, yes. So, and those end up being very fragile for kind of intuitive reasons.
Sorry, the vertical axis is...
Where? Here.
Yeah, let's say the vertical direction is the chi-square.
Yes, but you have to take these cartoons very, very unseriously.
No, yeah, but just to... So let's say, are there situations in which the plateau that you are describing is far away from the minimum?
I'm sorry, which plateau?
I mean, you are
the zero chi-squared solutions.
I mean, there is a region in which, okay, no, maybe I'm misunderstanding. There is a region in which, let's say, the red region there,
yes,
it's a sort of plateau, right? Because
that's the space of zero chi-squared solutions. So it's literally the bottom. You can't go lower, right? It's a positive function. And you're overparameterized, so this exists.
And you don't have regions in which, let's say, the chi-square is non-zero, but it is quite stable, and so it's hard to move out from
Probably
there.
true for many problems, yes. And I think actually when people study problems like this, they find that this is one of the reasons why stochastic gradient descent helps, because it kicks you away from flat intermediate points.
Okay. The reason why I'm asking is because instead is the typical case when you do the quantum. So this is what.
Yeah.
Okay.
Yeah. Okay. So these things all seem to conspire together to give you good descriptions of your unknown function from, very many parameters compared to your data. But there are still big gaps in our knowledge, obviously. So one of those big gaps is that all of this story depended a lot on the structure of the space of perfect solutions, right? The space of places where the chi-square can be exactly 0. And in linear least squares, this is a hyperplane. We know everything we could want to know about it. Mathematicians can really prove things about these algorithms on linear least squares because of the hyperplane things. But machine learning is not linear least squares. It's non-linear least squares. The functions are very, very non-linear. And we know extremely little right now about even what the space of perfect solutions looks like in simple kind of neural network models. The state of the art is that people kind of just train the model twice with 2 different initializations. They find 2 different zero-cost solutions, and they try to throw a rope on the landscape and see if it finds other zero-cost solutions. And they conclude, okay, it's connected easily, or you can't say it's not connected if you don't find it, but okay, you can kind of say, well, we didn't find it. These are very, very rough ways to try to reason about what the structure of the space of solutions looks like. And so the question that I'm going to now move into kind of my research on is, can we do better in nonlinear problems? Specifically, I'm going to introduce a very, very simple model of nonlinear least squares at describing what this space of solutions looks like. And then, hopefully, with future work, we can start to connect what we know about the structure in these cases to how these algorithms and models and the specific data that we pull interact with the quality of the solutions you get by doing these things. So here is a very, very simple model of nonlinear least squares. It's a model that doesn't really have a ground truth function. The ground truth function is, say, take random data and map it to a constant. It's the stupidest thing you could imagine, but it's a very simple model, and we can control it theoretically quite well. So the data is just, it's tensors with p different dimensions. So like p equals 2 would be a matrix, p equals 3 would be a 3 tensor, et cetera, full of random Gaussian numbers. And it maps from this space, the x's are these tensors, and the y's are just the constants. Okay, so it's a very, very stupid model. There's really no ground truth here. This is really just, can we describe in a nonlinear case what this set of solution looks like? The parameters are a vector in n-dimensional space. So the number of parameters is still n, right? And the model is that you take a polynomial in the parameters that's homogeneous of degree p, where the coefficients in the polynomial are given by the tensor elements. Now this is very stupid, again. Why is it an interesting model to study? Well, it's the simplest model of nonlinear least squares for a reason. It is nonlinear in the parameters, right? It's a polynomial in the parameters, not linear. But it is linear in the data. Sorry, it's linear in the data. And this is very nice, theoretically, because linear in the data means that there's a lot of simplifications in the theoretical treatment of the thing. So this is really the easiest thing to study theoretically you could write down with a nonlinear parameter dependence. And so the cost function is you take m data points, so you make independently m random tensors. You want to find some function through this polynomial, maps them all to the same constants. And the question is, what does the set given by chi-squared equals 0 look like? Can we answer that question? What can we say about it? And then maybe, eventually, how does it relate to dynamics? So this model sounds very stupid, but it had a lot of attention recently. These are all papers about this model. People have asked a lot of different kinds of questions, like, when does chi-squared have solutions, both zero-cost solutions and where do different kind of suboptimal minima lie. I've written about when this model has very flat minima, which can trap you, for instance. People have done dynamical mean field theory to analyze how gradient descent, and in fact, even stochastic gradient descent, behaves on this model. And in fact, this is the first model that has a dynamical mean field theory where people have shown that the stochastic gradient descent outperforms the gradient descent. So it reaches the solutions faster. And this is the very first time we've ever had this theoretical control, let's say.
So just to see if I'm still on the page, is it possible that a solution with chi-square non-zero is better than some bad solution in chi-square equal to 0? In principle, yes.
Sure,
am I
sure,
right?
yeah,
I'm
of course,
understand.
of course.
Okay,
Yeah, I mean, if you have a noisy function and your basis happens to contain the function exactly, okay, this is a trivial example, but again, it depends on the data, it depends on the basis. Typically, we don't expect that our basis contains the function. So, all right, so this presentation is about trying to describe what this manifold looks like. So the simplest thing you might ask about what the manifold looks like is it one connected piece or is it many pieces, right? That's actually not a very easy question to answer. So okay, the set, the solutions, you can say, let's make this very concrete. We have a set. The set is defined by all of the points in space that obey that each of the functions with our data maps to the same constant. And I didn't say this aloud, but we also take, to kind of mod out a trivial aspect of the model, we require that the parameters have the same norm. So in this, because these are homogeneous polynomials, there's a trivial rescaling when, if you rescale the norm of the parameters. So this is a small detail. So everything lies on a sphere. Everything lies on a hypersphere. Yes? It is very related to the p-spin spherical model. If you have exactly m equals 1 of these constraints, you're looking at a level set of the energy of this p-spin spherical model. So to count the number of components, remember it's a manifold. So these are like pieces with many points inside of them continuously connected. So we're very good in this field at counting isolated minimum. So you have a point in the function with some stiffness in every direction. We can count those using a fancy formula that I've shown here. There's a lot of control over this. Many people have done this for decades. But how do we get at the structure of, in this case, where we have continuous pieces? Now, the thing that I've done recently, which I'm going to describe, is how to compute the Euler characteristic, which is a topological invariant of this space of solutions. That's what I'm going to describe here. So, what is the Euler characteristic? We need to know that. The Euler characteristic is a topological invariant. Unfortunately, it's typically a chi, which is the same letter they use in chi-squared. Please note, if you see chi without the squared, it's the Euler characteristic. It's not anything to do with the cost function. So the Euler characteristic of a manifold, you can think of it as being defined by a procedure whereby you tile the manifold. You can see this cow is made of little polygons. And then you do an alternating sum over the different dimensions of tile. So you take the number of vertices, you subtract the number of edges, you add the number of faces. If you have a higher dimensional thing, you continue alternating in different dimensions of tile. And at the end, you have a number. In this case, it's 2. And if we do the same procedure for a different manifold, we can do the same thing. We can, for a standard football, the patches on the football, we can make the same kind of count. And we find it's the same answer. And this is a result of the topological invariance. We know that the cow is homeomorphic to the sphere, and so we should, in fact, find that these two things are the same. And so one of the results from the theory of, the topological theory of this invariant is that you can tile however you want. It doesn't matter how you choose to put down your vertices and faces, you'll get the same number in the end. And you can also, of course, deform your manifold however you like, you get the same number. So some quick crash course on facts about the Euler characteristics. We have a little intuition when I start telling you it has a certain value that's positive or negative. First fact is that, okay, this is something we all maybe learn in maybe a differential geometry class in university. If you have a connected, so single component, 2D manifold, this is where all our intuition can live, the Euler characteristic is directly related to the genus, the number of holes in the manifold, by a simple formula. So the sphere, simple sphere, is Euler characteristic 2, as we saw. Torus, 0, double-handled torus, -2, triple-handled torus, -4, et cetera, et cetera. So a very negative Euler characteristic for a connected 2D manifold has a lot of holes in it. Now, more general properties, because again, we're not working in 2D, we're working in high D. Any odd-dimensional manifold has Euler characteristic 0. This thing I'm going to start ignoring, so let's pretend I'm always talking about even-dimensional manifolds, because it starts to become very annoying to say it has this value except in odd dimensions. So rest assured, the work is quite consistent with odd dimensions always being 0. The sphere always has Euler characteristic 2 in even dimensions, of course. So 2, order 1 value for the Euler characteristic is consistent with like the sphere. If you take two manifolds and you take their disjoint union, so if you take two manifolds and take their union and they don't overlap, you just sum the Euler characteristics. Oh, I went backwards. So 2 spheres is 4, 8 spheres would be 16. So a large Euler characteristic can mean a manifold with many components, each of which are kind of sphere-like. But you can also get a large Euler characteristic through products. So if you take the torus is the product of S1 and S1. This is another way of seeing why the torus has 0 Euler characteristic, because S1 is the circle is an odd manifold, has Euler characteristic 0. So if you try to cross it with anything, you get 0 again. But in fact, I think for Occam's razor reasons, in the cases I'll be studying, which in a sense we're taking constraints and slicing different pieces of a sphere with different constraints, large Euler characteristic is much more likely to mean a big sum than a product, some kind of strange product manifold. So examples, many spheres, big Euler characteristic. Another example, S1 by anything is 0. So 0 doesn't mean there's nothing there. It means that you have a manifold with no Euler characteristic. All right, so why is the Euler characteristic computable when the simple count isn't? Well, there's a very, very nice, very beautiful mathematical theory, which actually, you can pick up these books. You don't need much more than undergraduate calculus to understand these things. This is called Morse theory. And Morse theory makes a mapping from Euler characteristic properties counted in tilings and things to properties of arbitrary smooth functions defined on the manifold. So if you take a manifold, here's the sphere. It's been kind of warped a little bit, but it's still topologically a sphere. And you imagine a function defined on it. So say that function is just the height on the sphere, right? The function starts at 0 at A, and it gets bigger and bigger at each slice until at the very top, I don't know, it has some other value. And you can define gradient flow on this manifold using this function. You just follow the gradient down. Now, this flow has critical points. The critical points are the places where the gradient is 0. And in fact, the flow field of gradient descent on any manifold, generically, so unless you do some very fine tuning of the function, it defines a tiling of the manifold. So here we have some vertices given by the critical points. We have edges given by the flow that goes directly between two critical points of difference in index exactly 1. And we have faces given by flow between critical points whose difference in index is exactly 2. And in fact, if you take this, set of flow fields between critical points of different index, you see that it makes a tiling, right? We can use this to define the Euler characteristic by taking the number of vertices minus the number of edges plus the number of faces. And the final contribution of Morse theory is to say, you can go one step further. Because of restrictions on the topology of this flow field, you can map the sum, alternating sum over the dimensions of the tiling to an alternating sum over the number of vertices of given index. These give you equivalent answers. And so you can get to the Euler characteristic by just taking an alternating sum over how many vertices how many critical points you have in this arbitrary function, doesn't matter how we chose it, on the manifold. And I told you we know how to count critical points, so that's the key thing. So this is the most technical slide, I'm sorry about it, but just very quickly to understand one last time exactly how this calculation becomes tractable. So imagine we know how to count critical points. So we can take our manifold, our chi-square equals 0 manifold, which I've drawn on the sphere here is a little wobbly manifold, and we pick some height function. So in this case, the simplest height function I could think of is you pick a vector, and you look at the inner product with a point with the vector, right? It's like a height, where the y-axis is defined by the vector. And then, once you define the function, you now have critical points, right, of this function, which are the minima. In this case, it's a two-dimensional thing. The minima and maxima of the function restricted to the manifold. And you could do this alternating sum. Of course, in this case, you get 0 because this is an odd-dimensional manifold. It doesn't matter how you choose the height. You could choose a different one. It's completely arbitrary because this is an invariant. If you choose a different function, a different height function, you get a different critical points, a different number of them for each individual type, but the alternating sum will be the same. And in fact, to actually do this, in the theoretical setting and high dimensions with mean field theory techniques, you get this alternating sum property for free, because in fact, in the normal case of counting all of the critical points, you do a lot of work to make sure that the critical points sum in your integral over the manifold in a coherent way by having to control this delta function. Let's see, that was forward. Here we go. Having to control this delta function here with the absolute value sign. But in fact, because the determinant of a Hessian of a function has a sign given by -1 to the index of the critical points, you can, for free, get the Euler characteristic of the manifold by just dropping the absolute value sign. So all we have to do is take a kind of procedure, which, okay, this looks mysterious, it's a crazy-looking formula, but I've told you that we're able to treat this in a harder case with an absolute value sign. And as long as we make sure that our integral is restricted to this manifold, we can compute the Euler characteristic using the same technique. So what are the results of this? So the simplest place to look at results are when we have a so-called p equals 1, which is a linear case, right? It's the same as linearly squared because our model was just order p polynomials with random data mapping to a constant. So if p is 1, then we don't have a nonlinear thing, except it is a little nonlinear because I said we were on the sphere. So the one difference between linearly squared and this is we're on the sphere. And so what we expect to find in the simplest case with p equals 1 is that we want to see when m different hyperplanes successfully have a non-zero intersection with the sphere. So when you try to intersect a hyperplane with a sphere, you have two possible outcomes. You can either miss and you have no solution set, or you can hit and you have a solution set which is also a sphere in one fewer dimension. This is, S2 becomes S1. And if you continue to add hyperplanes, you can, again, either each time miss the manifold that currently exists or hit it and get a sphere in one fewer dimensions. And so in this regime, you always expect to either find no solution, which is Euler characteristic 0, empty set, let's say, or that of the sphere. And in fact, this is exactly what you find. You can see the phase diagram and the key to the phase diagram by the colored spheres. When you have the linear case, as you change parameters, alpha is the ratio of the number of data points to parameters. So alpha less than 1 gives you a overparameterized case. As you change alpha and the constant that you want all these random functions to be mapped to, you find some phase diagram, and this phase diagram matches exactly with the results of previous work describing when solutions exist. So when solutions exist, it's a sphere. We could have, again, I sort of described this from first principles. In the little cartoon here, it's a manifold with very simple boundaries. Ooh, little cartoon, a manifold with very simple boundaries. Or it's nothing. You've got a manifold with nothing in it. But we're not interested in linear cases. I told you, they're all hyperplanes. In this case, all hyperplanes slicing spheres, so spheres. It's more interesting to go nonlinear. So what do you find in general nonlinear? Well, here we find 3 new different phases possible. So we can find in some regimes that the Euler characteristic is very large and very negative. So very large and very negative is at least consistent with, I'm going to use very careful language here, a manifold that is full of holes, Swiss cheese. It's a thing that has very non-trivial homology groups because you can snake lines around it in all kinds of funny ways. So full of holes. And in fact, the calculation, for a technical reason that I can get into in questions but not now, shows 2 different possible phases that are full of holes, a very negative Euler characteristic. One where the sort of closest part of the solution set to a random point is simple, topologically, and one where the closest point is all kind of funny and fuzzy. And finally, you can also find a situation where the Euler characteristic is very large and positive. And in this case, this kind of simplest interpretation of what you see, which must be true in certain situations, is a manifold that has very, very many components. And so, with this interpretation, let's say, of the results, which are, the direct results are the value of the Euler characteristic, positive, negative, large, 0, you can start making phase diagrams for nonlinear least squares problems of this very simple form with homogeneous polynomial data of various kinds. So this is quadratic problems you find as a function of the constant you'd like all the functions to map to, and alpha, different phases at different values of these things. As you change the order of the polynomial, so p equals 3 is cubic, p equals 4 is quadratic, etc., you find, okay, different phase diagrams. It's not that, let's say, this structure is interesting that we can describe it, but right now we don't have a lot to say except that we can describe it. Finally, I mean, all this treatment can also equally well describe cases that have inhomogeneous polynomials, so arbitrary combinations of polynomials. So here, if we consider kind of a linear combination of a linear part, which of course has the sort of trivial description that only has 2 possible phases, and a quadratic part, which has this other description with 3 possible phases, we can see how the phase diagram gets warped as you add small amounts of nonlinearity, let's say, and where different phases enter and how strongly they do, and in what parameter regimes we have to find them. Now, this is really the end of my results, but it does lead to a lot of future questions related to some of the existing work of colleagues of mine in these exact models, which are, so given this, so first, how can we calculate other interesting properties? For instance, if we just really want to know the number of components, and I can stop making euphemisms about how the Euler characteristic means a certain thing with respect to the number of components, it would be nice to figure out a way to actually count them, but this we don't know how to do yet. But also, the big question, which I motivated in the entire front of the talk, is how this interacts with dynamics. I'm currently in talks with a colleague of mine on comparing these phases to the results of dynamical mean field theory and different regimes of behavior. Unfortunately, right now we're bound by the precision of dynamical mean field theory. So we're working on some hard, boring numerical things to try to resolve this. Of course, it'd be more interesting to know in a problem that actually has some non-trivial structure, which has a ground truth which is interesting, how these phases behave. If there are new phases that exist, usually when you add a sort of signal to your problem, you don't just have random noise you're fitting, you also have a ground truth you're trying to find. You do find new interesting structure and new behavior sometimes as you interpolate between 2 regimes, one where you can't find the ground truth and one where you do find the ground truth. Versions of this model which have such a non-trivial ground truth will be interesting to begin to study. And of course, finally, once you have the ground truth, once you study dynamics, you can start to ask, how do these properties, how do this, can we quantify these things I said in a hand-wavy way about stochastic gradient descent, finding high entropy places that work well to describe problems? Can we start to quantify that in simple scenarios? Say, it does work for this problem, it doesn't work for this problem, and begin to continue, begin to progress on explaining why this set of features that we are lucky enough to see in existing machine learning applications actually work to produce good overparameterized fits. And with that, I'd like to stop my talk. You're welcome, by the way, you can play, I wrote a code in C++ to generate all the figures for the fits. You can go and play them yourself if you want to. If you don't believe me that I actually use gradient descent to generate those. I mean, really, it's very simple, maybe 200 lines of code. And that's it.
Thanks a lot for this talk. Questions? We already had many, but I'm sure there will be more.
Thank you very much, Jaron. So do you ever care about the global minimum, or your desired solution is always a local minimum, and the global minimum has nothing special about it?
Well, in the case I'm describing here, we're always talking about global minima, because we're talking about the 0 cost, chi-squared equals 0 identically. Chi-squared is a positive function. So this in the overparameterized case, you find, when you're not blocked by local minima, you find these 0 parameter solutions. Now, it is an open question, in what regimes of the problem do you actually find the bottom of the landscape, the 0 cost solutions, and when do you get stuck in local minima? This is something that people are working on, including me right now. So at the moment, the questions are a little more basic of like, not, again, this problem has random data, and so you can't really say something about the quality of the solution. We're asking simpler questions like, under what circumstances do you find zero-cost solutions? What circumstances do you find local minima? And then, of course, iterating on the model, making it more structured, we can start to ask questions like, do the local minima have qualities that we desire, or do the ground states, the zero-cost solutions have qualities we desire, and what are the structure of the desirable ones versus the undesirable ones?
Thank you.
I had going back to the error bar. So you said error bars are related to weightings, but let's suppose there's just some uncertainty in these data points.
Yeah.
So then the chi-squared can be 0, obviously, for one choice, but if you go a little bit away, it's no longer 0.
Yes.
Is there some way to optimize that so it's the lowest chi-squared on the average for all of these?
So if you have multiple sets of data.
Well, it's not multiple sets of, if you want to think of it that way, it's just the uncertainty in the data point. So in real life, data points are not exact, right?
Yes, it's true. I mean, in some sense, okay, there's kind of two answers to this. One is not going to be satisfying to you as a physicist. One answer is in machine learning, people, they don't have uncertainty and they have no way to quantify it, right? The data is pictures of cats or something. And the question is, how do you put error bars on that? I mean, you have properties of the camera, you can do engineering about, but in the end, they tend not to care because, again, we're in a regime where we perfectly hit every data point, right? Every data point is perfectly fit by the function. But we don't actually care about operating, and because we hit every data point perfectly, the thing that we fit is it behaves very strangely in the vicinity of a data point.
Sorry, a data point, let's say it's a photo, then it's something
exactly. So
black
if you're,
or white, let's say.
Exactly. So if you're very close to one of the things that you trained on, one of the photos that you actually saw in your data set, then you see kind of little strange things that, you see improbable, bad fit things nearby that because the function is going out of its way to get to the data point. But again, you have to remember, in these problems, this is a very big cartoon, right? Everything projected to one dimension might as well be bullshit, because in high-dimensional cases, you are really, really unlikely to ever find yourself nearby a given data point, right? To have every pixel of a big picture, even just say plus or minus 1, be anywhere near one of the training things that you offered the machine learning algorithm. And so to describe well the area between the data points is much more important than having a weird little spike in your functional approximation that goes through it. The other answer to this question is, this is essentially what the statistical measure of variance is in the quality of a fit, right? So as a statistician might judge the quality of a fitting procedure by taking their data, understanding it has a certain uncertainty they can estimate, and then adding noise with that uncertainty to the existing data and seeing how much the fit varies as you do this. So this is how you would measure the variance experimentally, and people do care about this, but in machine learning, they really, really, really don't care. They don't want to hear about this at all. I mean, again, they figured all this out without knowing why it works. They just started, taking more and larger models, saying, what if we tripled the parameters? What if we made it bigger? And it worked. And now we're picking up the pieces. Why does this work? It's very unsatisfying that it does.
Perhaps a silly, or let's say, I'm not even sure it's a well-posed question, but to me it looks that in all this business you are, as you said, you are working on a cost function that you are unsure that is a good cost function, in the sense that, are there attempts to modify the chi-square in a way to include, how can I say, a penalizing if the solution is not good in any sense? Like, I don't know how to formulate the question, but you know what I mean, right?
I know what you mean. People do think about this mostly in research. Because we want to, in fact, an example of this is literally this, right? One way you might modify the chi-squared to make better function is to add explicitly a regularization. But again, making a very careful modification of the chi-squared to prefer better functions is kind of a dead end for the actual engineering side because no one computes the gradient. People rely on really very coarse approximations of the gradient that happen to do a better job than the gradient would have done. And so rather than make a lot of effort on the engineering side to come up with very clever ways to make make a unique good solution in your chi-squared problem by regularization or something like this, people say, we don't care. We have algorithms which do this for us. And now, a mathematician tells them 10 years later, hey, there's a deep reason why this is doing this for you. But they don't care. They just, say, look, like, for this neural network, it doesn't work. We don't use that neural network. For this neural network, it does work. So we use it. And now we're starting to pick up the pieces and say, look, that neural network has high entropy solutions that are bad. And this neural network, for whatever reason, has high entropy solutions that are good. And that's why your algorithm, which is a set of teetering approximations, does do a good job with that neural network.
Okay. More questions? Okay, if not, we can thank Jaron again.
I hope it was satisfying.